Hi Science2 kiddos. I'm going to show you some of the math behind calculating gravitational force. This relates to chapter 5.5 in the Hewitt textbook. But before we talk about that, we have to talk about calculating what's called the gravitational constant, which is a number that sort of puts gravity in context and brings newtons into the math. So we'll define it really quickly. I'll use that same gravity force FET simulation you did for homework to then do some of the math. And if you feel up to it, as an optional extra credit challenge, you can try doing one of these math problems on your own. Again, this is sort of more at the honors level in terms of the math, but you're welcome to give it a try if you want, but I won't require you to do it. So chapter 5.5 in Hewitt defines the universal constant of gravitation as a very small number that represents the very weak force of gravity, right? We often think gravity is being very powerful, but it's actually technically a weak force. It also brings newtons into the equation, which is the unit used to measure force, and again, it relates it to the mass and distance equation that we saw from Newton earlier, right? We've talked about this before, you've read about this. Here's your gravitational force. We can see that it is directly proportional to mass, right? The larger the mass is, the more gravitational force, right? Earth exerts a lot of force on us because Earth is very massive. But it's inversely proportional to distance, right? The farther away you get from an object, the less gravitational force you're going to feel from it. The farther away you get from Earth, the less gravitational force you feel from Earth. They define the gravitational constant as being equal to the force between two 1 kilogram masses 1 meter apart. So imagine you had 1 kilogram mass and a 1 kilogram mass exactly 1 meter apart. Sort of like in that simulation, but these are on a much smaller scale. What this means is that the gravitational force that these two masses would be exerting on each other would be equal to that very small number right there. And so we can rewrite that in scientific notation form as 6.67 times 10 to the negative 11. Again, that negative 11 there tells you it's a very, very small number. Gravity is a very weak force. It also has a crazy unit on it, newtons meters squared per kilogram squared, but you'll see in the math where that comes from. So I took a screenshot of the FET simulation in its standard setting, and I want to see now is this accurate? Can we actually calculate the value for the gravitational constant g using these numbers? If it is accurate, the answer I should get is right there, 6.67 times 10 to the negative 11. And so we'll see if that's the number that I actually get from my math. So to plug in the numbers, the force, F, is right here, 33.4 newtons. And again, I know force seems to be given twice, but notice that it's always the same number, right? The force is always equal, so that's what we'll use there in newtons. Mass 1, you can see right here, is 2 billion kilograms. I'm going to rewrite that as 2 times 10 to the 9th kilograms. That's billion right there. Mass 2 is right here. It's going to be 4 billion kilograms. That would be 4 times 10 to the 9th. And the distance between them is going to be 4 kilometers. But you'll notice in the gravitational constant, the distance is actually in meters. So we can't use kilometers. We have to convert that into 4,000 meters. That's how many meters are in 4 kilometers. So if I plug those numbers into the equation right here, again, this is using the same equation, just plugged in all those numbers, it looks kind of complicated. So I want to get g by itself. I want to simplify all these equations down. So we'll start off by multiplying the masses by each other, right up there. That's the first thing we'll do. And then we'll square the distance between them. That's the second step of the math that we'll do here. Now, working with scientific notation can get kind of tricky. These are really, really big numbers. And there's a useful tool in your calculator called the E function. You have to hit the second button and then your comma button, and it types a little tiny capital E. And what that means is it's whatever number you type first times 10 to the power of whatever number you type after that. So for example, here 3.6e5 is actually 3.6 times 10 to the 5th. And it also tells the calculator to do that as a single operation. So you don't have to type brackets around them if you don't want to, though I think it's always good to use brackets on a calculator. So to multiply the masses by each other, that's what you need to plug into your calculator right there, 2e9 times 4e9. That's just 2 times 10 to the 9th multiplied by 4 times 10 to the 9th. And it spits out 8e18, which means 8 times 10 to the power of 18. Very big number. And on the bottom here, when you do 4,000 squared, you're going to get a big number, 16 million. So I rewrote that in scientific notation form here too, just to be consistent, and it's also an easy number to work with. So again, I'm going to put that number here on the bottom in place of that equation, and I'm going to put this number here on top in place of that equation there. So again, you can see now our equation is looking a little simpler, right? I just took the answer, multiplied my masses, and squared my distance. Now notice the units have now changed. I now have kilograms squared here because I did kilograms times kilograms, and I have meters squared on the bottom because I did meters times meters. So I could divide these numbers and then divide both sides by their quotient, but I want to show you what's going on with the units. So what we're actually going to do next is get rid of this bottom number here. To get rid of the distance between them, we're going to multiply both sides by that same number. So I'm going to multiply the top by 1.6 times 10 to the 7th meters squared, and I'll also multiply this side by that same number as well. So here's what that looks like. You can see again I've got 1.6 times 10 to the 7th on both sides. So again, think of the equal sign as sort of the separation point. On this side, you'll see that 1.67 and 1.67 will cancel out, right? If you divide one by the other, you get 1. And meters squared will also cancel each other out. So now we've just got g times 8 times 10 to the 18th left over. On this side, I've got to solve this. I've got to get the product, multiply these two numbers by each other. If you type that into the calculator, it's 1.67 times 33.4. Again, you can see now I've gotten rid of my, right, we've simplified that side there. And so if you punch this into your calculator, it gives you a really, really big number, 534,400,000. Let's write that in scientific notation. Again, to be consistent, it's also easier to work with, 5.344 times 10 to the 8th. And again, that is now what I'll put here, because that is the product of multiplying those two numbers by each other. All right, so here is what's left. Now, this is looking a little simpler. You'll notice the units are doing a weird thing, because since we multiplied meters squared times newtons, we haven't really canceled anything out, and so the new unit is literally newtons meters squared. To solve this now, I just need to get g by itself, so I'm going to take that, and I'm going to divide both sides by that same number, right? So we need to cancel that out, essentially. Here's what that looks like. So dividing both sides by 8 times 10 to the 18th, again, you'll get 1 here, right? They'll cancel each other out, and kilogram squares cancels out. And then you just need to find this quotient. Punching that into your calculator looks like this, 5.344E8 divided by 8E18. Your calculator gives you this, 6.68E negative 11. Again, don't forget that negative there. It means it's a small number. 6.68 times 10 to the negative 11. So that is what our g value equals, right? We should now have g by itself. And we'll bring this over here again. That is the quotient of those two numbers being divided. So there you go. I found that g is equal to 6.68 times 10 to the negative 11. Again, notice I divided my Newton meter squared and I divided by kilogram squared, so that's where that weird unit comes from. And you can see that I was pretty close to the true value of g, right? I was just off by about a decimal place or so, but I'm okay with that. All right, so now let's use the value of g to see if we can solve for the gravitational force. So here's a new setting. You can see I've changed the masses here in this screenshot and the distance. And this time I'm going to use the same equation, but now I want to solve for F, the gravitational force, because I already know the g value, right? And that's always going to be given. That's always the same. It's why it's called a constant. So what I should get is that, 41.7 newtons. I know that's the answer that I'm trying to get. But again, if this is accurate, if we're using g correctly, if I do the math correctly, that's the number, that's the answer that I should get. So again, we've got a distance of 5,800 meters. And our masses now are going to be, mass 2 is 3 billion kilograms, and mass 1 is 7 billion kilograms. So again, just going to plug that into the same equation. So there you have it. Again, I'm still working with the same equation here. But this time, I've plugged in the g value as well, right? So there's g. And we've got mass 1, mass 2, and distance. And again, what I'm trying to find is F. And again, I should get that same answer there. 41.7 is what I'm going to try to go for. So just like we did before, let's go ahead and multiply our masses by each other and square the distance first. So we'll do masses first, distance second. Here is what you should type into your calculator to multiply the kilograms by each other, and that's the answer that it will give you, 2.1 times 10 to the 19th. If you square 5,800, it gives you another really big number, 33,640,000, and we can rewrite that again in scientific notation. So let's go ahead and replace those top and bottom numbers now. So that's our sort of simplified fraction with our answers in there. I know that it is now 2.1 times 10 to the 19th kilograms squared, and 3.364 times the 7th meters squared there. Now again, we don't need to try to multiply this out to f or anything. I'm just going to go ahead and solve this fraction now. So I want to divide those numbers by each other. Again, just showing you kind of simplified form. Let's solve this, right? We're going to divide those numbers by each other. In your calculator, here's what that looks like. So to type that into your calculator, it looks like that. 2.1e19 divided by 3.364e7, and it gives you 6.24e11, or 6.24 times 10 to the power of 11. So I put that there in place of the fraction now. And so, finally, to solve for f, all we need to do is multiply these two numbers by each other, right? Let's get the quotient, or the product. And what I like is you can really see here how the units cancel each other out. Because I divided kilograms by meters, I've got kilograms squared per meter squared as my unit over here. And I still have that unit from the gravitational force constant, but if I've got meter squared on top and meter squared on the bottom, they're going to cancel out. And I've got kilograms on top and kilograms squared on the bottom, they're going to cancel each other out, and all we're left with is newtons, which is exactly what force is measured in, so that works out. So to type this into your calculator, we're just going to do 6.67e negative 11 and 6.24e11. And if you multiply them in your calculator, you get 41.6, which is a nice small number compared to what we've been getting earlier. And so that is your value for f. And you can see that I was pretty close. All right, I got 41.6. We know the true value was 41.7. So again, I was off by a decimal place, but I'm okay with that. Not sure, maybe I'm rounding in the math somewhere. And again, the unit that's left over is newtons. So your challenge now is, if you feel like you were sort of grasping the math there, for 5 extra credit homework points, you can try solving for F, the gravitational force, in this example here. You can see I've covered over the force. Now, yes, you could go to the simulation online and punch in these masses and set this distance, and it will give you that answer, the correct answer there. But I want you to show your work. So you can do it on paper, take a picture, and send that to me, or you can use a program like this where you can write on the screen if you've got the mechanism to do that. Send that to me, just as long as I can see the work you did and how you solve for it, and then I can give you the extra credit. Thank you.